Hello everyone, thank you for joining us and joining my presentation here today. My name is Leonardo Pichel. I'm a postdoc at the University of Bergen, and today I'll be presenting my work here using geodynamic modeling to investigate the link between rifting and rifted margin architecture with soil deposition and passive margin soil tectonics. I want to thank you, the organizers, and also want to thank you guys for joining the presentation. And I also would like to apologize for having to record this presentation, as at the moment I'll be flying. I'll be in the middle of a flight. So yeah, thank you everyone for understanding this. And yeah. Hello everyone. So one of the key motivations for understanding or studying soil basins is the economical significance. And the societal impact as well of salt basins. So salt basins, they are economically important. They are historically famous for hydrocarbon exploration. For example, some of the largest hydrocarbon provinces in the world, they occur within salt basins. And many of those plays are related to soil tectonics, so they are controlled by soil structures. So the largest and perhaps most important or economically important salt basins, they occur in rifted margins. They are salt-bearing rifted margins. And these salts in these margins, they are interpreted to be deposited in the last stages of rifting. So 1 or 2 million years or up to 5 million years before breakup. And some of the examples include the South Atlantic, so the Brazilian margin with Campos, Espírito Santos, and Santos. The entire West Africa margin from Gabon to Benguela and Namibia, and also Nova Scotia, Morocco, the Gulf of Mexico, and the Red Sea. And the other motivation for this work is because the link between margin scale, rift architecture, and evolution with salt deposition tectonics hasn't been extensively investigated, or not investigated at all using geodynamic models. So there are a lot of unknowns, a lot of things are not fully understood. For example, the nature of the basement underneath the thick salt, especially in the distal margin. We have a lot of seismic imaging issues related to salt. So imaging things underneath thick and usually highly deformed, highly heterogeneous salts. The beginning or the onset of salt tectonics and what are the controlling processes through time and how they interfere or interplay with each other. And the dynamics of soil deformation. And so we believe this is mainly related to the lack of a geodynamic modeling approach that combine both rifting with soil deposition and soil tectonics. And a lot of the present day modeling studies, some of the ones I also been working with in the near recently, we prescribe basin geometries, we prescribe a lot of the processes that we infer occur in these basins. And with this approach, with this geodynamic modeling approach, we allow a more self-consistent evolution of salt basins. And that can be highly beneficial to understand what are the processes, what are the dynamics of these basins. So the basics of soil deformation in passive margins, so the main process that control those styles of this style of deformation, soil tectonics, is thermal subsidence. We have denser oceanic crust that produces subsidence, greater subsidence in the distal margin, and that produces a seaward tilt of the basin, and that drives lateral salt flow. And this lateral salt flow produces up-dip extension and down-dip shortening. The other processes, so the two main processes that control this type of deformation is differential loading. Differential load is driven by progradation of sediments, so you have these wedge-shaped depositional geometries that produce greater loads in the proximal parts and smaller loads in the distal parts. And that also produce lateral salt flow. And these two processes are related or described in our community in the literature as gliding, thermal subsidence as causing gliding, and spreading driven by differential loading. And both these processes, they create what we call kinematic linked deformation. So we have domains of deformation. They are kinematically linked as salt and overburden move laterally. We have these kinematic link domains are the up-tip extension domain. We have an intermediate translational domain that has relatively less deformation. If you have a well-behaved salt with a very flat base salt, you should have limited deformation in the translation domain. And the shortening domains, domain will have buckle folding, thrusting, or diapiece being squeezed. And this sort of lateral system, this lateral tectonics, is controlled by quiet flow. So quiet salt flow, the velocity of flow increases towards the top of the salt layer, towards the top of your viscous fluid. And this also produces movements of the overburden. So the overburden moves at the same rate as the salt, as the top salt. The other type of flow is Pichel flow, and that doesn't require any overburden movement or lateral movement. In this type of flow is greater in the center of your viscous fluid, in the center of your salt detachment, and salt is expelled or moved laterally from underneath thick sediments towards areas that have less load. So have greater load in the proximal domain and expel salt towards the distal domain, and that where the salt inflates and rises. So these are the two main processes and two types of flow we see in passive margins and salt basins in general. Another problem with salt tectonics in these settings is that because salt is very fluid, it's very dynamic and produces diapiers, and also dissolves, a lot of the deformation can be cryptic. So sometimes what we see in the present day structure, we can't really constrain how much shortening or extension you have in any specific diapier structure. So a lot of the deformation in salt tectonics can be cryptic, and modeling or restorations are really useful to constrain that, but there are some limitations, of course. So for this, we think our type of work we use in geodynamic models can be helpful. We use Phantom, which is a 2D thermomechanically coupled numerical model. It's a whole lithosphere scale model, so 600 kilometers of depth and 1200 kilometers of width. Because we focus on the post-salt and passive margin, and we're just gonna show the first 40 kilometers of vertical length of the model. And in this work, so I'm not gonna present a lot of details of the of the physics of the models. These have been published extensively in the literature, but I'm gonna show what we do that is new. So we use 4 different types of crusts, and that produces 4 different types of margins. And we see how salt tectonics vary between these different margin types. For that, we use different crustal strength profiles. So we have a very strong crust here, M1, which gives a narrow margin, and the other end member is a very weak crust, which gives an ultra-wide margin. So these produce conjugate rifted margins. They're usually relatively symmetric. There is a level of asymmetry, but in this setup, they're usually relatively symmetric. For the sedimentation, we use a gradation for the pre-salt and the salt. As I mentioned, the salts in these models, they are deposited in the final stages of rifting, so approximately 1 to 2 million years before continental breakup. We have a relatively low sedimentation rate for the pre-salt and a high sedimentation rate for the salt. And the salt is also deposited just during 1 million years. So these rates and the timing and the base level are consistent with nature. So the salt is depicted to be deposited relatively rapid, fast in the last stages of rifting. And for the post-rift, we have progradation. So we have a progradation approach that allows a dynamic change of the profile with the underlying topography, and that produces a more realistic, we believe it produces more realistic stratogeometries. For all these models, the progradation rate is the same, it's controlled by sediment flux number, and it gives a relative rate of progradation of 2.4 kilometers per million year. This is the initial salt basin configuration, so we have narrow margin to ultra-wide margin in the bottom. Of course, with the increasing width of the margin, we also have increasing width of the salt basin, and we also have increasing salt volume. The other aspect that is interesting is that narrow margins have increasing base salt topography and disconnected, and the salt basins are partially to fully disconnected between each other. So you have, for example, salt basin 1 and 2, they are disconnected in the narrow margin, and here you have some fully to partially disconnected salt basins. And in the wide and ultra-wide margin, the base salt relief is more subtle. It does produce some segmentation of the salt bases, but they are not fully disconnected, so they are largely connected. I'm just going to show the final stages of each model. So narrow margins, we have these 2 fully isolated salt basins. we don't have significant lateral movements of the overburden. The salt moves laterally, but is also limited by this distal high. So the sub-basin 1 doesn't connect with sub-basin 2. And deformation is mostly vertical salt tectonics. You have upright vertical diapias with this bowl shape or wedge shape mini basins. We don't have significant rollovers or normal faults or contraction of shortening. We have a salt snap that is approximately 24 kilometers wide and with some salt anticlines, but very subtle salt deformation. And we have a expulsion rollover here, but this is just related to lateral salt flow, no overburden extension. Intermediate margin, we have no undeformed salt in the proximal domain. The salt is very thin and is rapidly covered by the sediments as they prograde. But we have more significant salt tectonics in the distal margin. We have a sort of hybrid rollover which accommodates some lateral expulsion of salt, but also some extension. It's a sort of basin-wide zipping rollover, so we have this small listric normal fault and a diapia in the footwall. And then we have a salt nap. It's a bit wider and it has similar style of diapias, but a bit more prominent diapias. We have just approximately 6 kilometers of extension within this rollover, so there isn't much extension going on there. So still with a sort of significant vertical salt tectonics and limited lateral salt tectonics as well. This is just a model that shows the evolution of this, an animation that shows the evolution of one of these models. So we see as we propagate the sediments, that produces load, and that load drives vertical salt flow and diapirism. Because of this prominence high here, we don't have significant translation. I can play it, just part of it again. And we see that there is a salt nap in the distal margin that forms immediately after breakup. This salt nap is actually a combination of stretching of the salt as you break up the crust, and then is amplified by salt tectonics in the post-rift. The wide margin has a completely different story, has a much more pronounced salt tectonics in general, both vertical salt tectonics, but more importantly, lateral salt tectonics, have very large rollovers in the up-dip domain. And these rollovers accommodate approximately 18 kilometers of extension. With this extension, the whole distal margin and the whole salt and overburden translate laterally. And you have a series of these squeezed diapias with complex shapes and mini basin geometries. Some of these mini basins, they rotate as they get buttressed over the salt high here. And you also have a very large salt nap. The salt nap is 36 kilometers wide, and you have a more simplest, you have a bit of simpler diapia geometries overlying the nap. So yeah, in this model, we have up-dip extensions balanced by translation and some diapia squeezing here. The nap itself doesn't really balance with that sort of that deformation. The nap advances by pressure-driven flow. And the ultra-wide margin, similar to the wide margin, is more like the wide margin on steroids. It's very big system salt tectonics. We have about 30 kilometers of extension in this more proximal domain. We have some more vertical diapias, vertical salt tectonics in this sort of proximal sub-basin. But as you move over the seaward zipping crustal raft, we have a lot of extension. So we have rollovers, turtle anticlines, and reactive diapias. In the distal margin, we also have diapia squeezing, which accommodates this extension from the proximal domain. And we have a very large salt nap, so about almost 6 kilometers wide salt nap. And that's a model, that's an animation that shows this model. So salt is deposited now in the final stages of rifting, and we see that we have a very thin salt, which is we call salt nap over oceanic crust, over a newly formed seafloor. And this salt nap, as I said, for the narrow margin, is also a product of stretching. This nap is later amplified by lateral salt flow and post-rift salt tectonics. I'll play that part again. So you see the nap already there in the oceanic crust. As in you prograde sediments, salt flows over this deep in base salt, and also the diapias are squeezed as the system translates seaward. So what we've seen so far is models with relatively thin pre-salt, but we also tested different pre-salt thicknesses or sedimentation rates. And what we see here is two end members, so very thin pre-salt and very thick pre-salt. With increasing pre-salt thickness, we have less accommodation for the salt, therefore we have thinner salt. And what that causes is that thinner salt produces less pronounced salt tectonics. So that's what we see between these two models. We have more complex diapias and more pronounced extension and nap advance with the thinner pre-salt. We also have a change in the basal relief, and you have a more subtle basal relief with thicker pre-salt, and that can also impact the kinematics of the proximal salt deformation. And to finalize this, I wanted to show a sort of separate project, which is actually our first paper, where we evaluate what happens with the salt basins at the inception and the onset of salt tectonics in rifted margins. So we use the reference model, which is the wide margin model, as a reference model with intermediate salt viscosity. And what we see is that there are a few interesting things that are relatively eye-opening. We see that the most distal salt is deposited during ongoing extension. So it's we have seen the position thickening within these more distal grabens, and we have what we call intra-salt mini-basins, or cinder position mini-basins. Right after breakup or with breakup, the more distal salt here is stretched and in place as an allochthonous nappe over oceanic crust. So this early nappe, which is about 15 kilometers wide in this model, is formed by a stretching of the salt as you break up these two basins, these two conjugate salt basins, and placed over newly formed seafloor. And then you have the subsequent evolution of the salt basin with the post-rift progradation and spreading and gliding, and have this fully established system of salt tectonics with up-dip extension, translation, and down-dip shortening. Down-dip shortening is mostly by diapir squeezing, and we have about 16 to 18 kilometers of up-dip extension, which balance with diapir shortening. The nappe is also amplified. It advances 11 kilometers further seaward. It also triples its thickness. It gets more deformed. But what we see is the nappe advance, the post-rift nappe advance, is unrelated to overburden extension. It's mostly driven by pressure-driven flow, or Poiseuille salt flow. And the nappe itself is a product of syn-rift stretching and post-rift pressure-driven flow. And this is a model animation that shows the evolution of these conjugates. Just gonna skip a bit further. So I have the salt deposit now as we're just about to break up the oceanic crust, and we see this very thin salt layer, allochthon salt, that's in place over the oceanic crust, and then is later advancing further with progradation and pressure-driven flow. So just to conclude, we see that the salt tectonics can vary significantly across different margin types, and those are primarily controlled by the salt volume, basal relief, and the progradation rate, so the relative rate of progradation. Because the volume is constant for each margins and the reef changes, the relative rate of progradation relative to the margin reef varies. So those control things like the nappe tectonics, the ratio between vertical and lateral salt tectonics, and also the amount of up-dip and down-dip extension and shortening. So I just want to leave with that, and I want to thank you everyone for joining, and I hope you enjoyed the presentation.